recording again. So this is now going to introduce myself again and again. So myself, Sipan Mandal. I'm working at ITBHU as a research scholar. My research field is solar physics, and as a PMRF fellow, I have this deliverable to conduct these live sessions. And today I am going to take the live session for week 10, where I am going to again solve the assignments given in the previous year, in the hope with the hope that this will be helpful for all of you, and when you are trying to you will be trying to solve the assignments for this year. So let us move on to the first question. So within the variational principle, the ground state energy can be can you tell me, show me through, what will be the correct answer?
It will be greater always. Greater than third
It
one.
can also be equal at some point.
Equal, yes. If there is one
If
option,
it
yes.
is greater or equal, this or two
If it is exactly the wave function, then it will be equal.
yeah. So this two will be the correct answer, right? Greater than or equal. Okay.
Yes.
So the next question is, suppose you expand the wave function in a plane wave basis using 100 plane waves and then 20 plane waves. Which of the following statement is correct? So the total energy computed by superposition of 100 plane waves construct the wave function is same as the total energy construct for the wave function constructed by 20 plane waves, and then it is greater, it is less, and we cannot comment on the total energy. So can you shed some light that which will be the correct answer?
I think there was a plot that was showing that it will be greater. I think it is increasing,
See,
decreasing. Forward. Actually, they drawn a graph, or plotted a graph.
so as the number of plane wave will be increased, so that is a better estimation or approximation of the total wave function. So that will give a total energy which will be much closer to the exact estimation of the energy, as we can find out
energy,
from the exact energy. So the total energy will be less, right, for 100 plane waves than what we will estimate by 20 plane waves.
Yes, it will be less.
So this will be the correct answer. Okay.
Yes.
Okay. So if we move on to the third question, so for the problem of potential oil with a finite depth, as discussed in the lecture, so you see the lecture, right?
Yes, I have gone through once.
So fine. So you can find out that if A, the periodicity of the plane wave, is increased, which of the following statements are true? So what happens is, you have initially a potential like this. That's a finite depth with a finite depth. This is a potential well. But whenever we are trying to do this by the iteration or the simulation, what I am trying, that I am going to take a periodic potential well, right? So it will have some periodicity, and that periodicity is depending upon the value A. Okay, so as A increased, what will happen, that the periodicity will be increased, and if A is lesser, then what will happen, that this will be just a one right. So as the A is increasing, so they are moving further, so the interaction between the periodic images will be decreased, right? Yeah. So this part is like increasing A means interaction between the periodic images will decrease. So this is the last two options. Now we have to find out which one of the these things will be correct. So the second part is clear, that if A is increasing, the interaction will decrease. So what will be the effect of that? So as the interaction is decreasing, So the lowest energy eigenvalue will be decreased. Okay, so you can find out that the lowest energy eigenvalue is depending up proportional to the interaction term. So I think this will be a correct answer. You can find out the lecture also. Maybe I am wrong at this point. I cannot
Okay.
recall this thing right now. Okay, so the next question is, so for the problem of the potential well with a finite depth that is discussed in the lecture, if we use v naught to be minus 1, so you can see the course also here that they are not using v
Yes,
naught
yes.
to be minus 1. This is just given a 1, right?
No, no, they are using minus one in the sense this is V naught is equal to minus one in the sense
This
total
attractive
is
potential.
minus one.
Yeah.
Yes.
So b is given to be 2, a is 15, and n is 100.
In the lecture, they are saying that V cannot be negative, but potential is minus V naught.
Minus b
Here
naught.
they have
Yeah,
printed as minus one.
minus 1, right? So if we find out this, so just a second, let me go to the browser to a better one. So just a second. This is the code. Is it visible to you?
Yes.
So initially these are all the things which are taken to be uh, taken under consideration for assigning the types of the variables, and then I'm going to assign the potential and b the parameter, and then it is saying that if v naught is this less than 0 or b naught is less than 0, then we'll stop our programming. So then I am going to write in a certain form the v naught and b. Okay, similarly it is asking for a and n value, and then we are going to give those values a and n, and it's saying that okay, if a is less than b, which we have already given initially, and then n is less than equals to 0. So n is basically the number of plane waves. Okay, so, and a is the periodicity, v is the potential, b is, I cannot remember exactly. Okay, so you have the total number of plane wave will be dependent upon n, and that is 2 to the power 2n plus 1. Okay, so if we are giving a value of n equals to 10, then the number of plane wave will be 21. Okay, then we have this arrays. One is k, e, worth, h. So these are the arrays which will be used at different stages while we are doing this programming. So we start with that kn1, that the first element of kn array is giving a value of 0. Then from the next element to the total number of plane waves which we are assigning, that okay, we are increasing our step by 2. So if we are starting from 2, the second step will be 4, then it is be 6, and then I am assigning that okay, kni, that means it is kn2, and then kn3, those will have this value. See if it is 2, okay, so 2 by 2 will be 1, so this is basically 2 pi by a, and this is basically minus 3 by minus 2 pi by a. Okay, so this way this is assigned. So again I am going to start a loop here. So do I equals to 1 comma npw, that is total number of plane waves, and j is also running from npw, and then if I equal j, so you are basically have a matrix. So when it is the diagonal elements, you are assigning the energy, sorry, the Hamiltonian, to have this kind of a value, that kinetic term, which is square minus v naught by a into p. So this is the term coming from the potential, and this is the term coming from kinetic. Okay, and that will construct our total Hamiltonian. And this hij, this is formulated as the diagonal element of the Hamiltonian. And else, if it is not diagonal, that means if I and j are not same, then we have the value of Hamiltonian in this form. Okay, so the details of these things can be found from the lectures. So okay, then L work is another variable which is defined to be 3 into Npw, that means 3 times of the number of planets. Then we are going to assign, or we are going to use a subroutine which is DSYEV. Okay, so that will have some parameters which are going to assign, we have to assign them. And it says that okay, and after calling this routine, it will do the diagonalization of the H matrix. So basically what happens, that you have a high Hamiltonian matrix, and to find out the eigenvalues, what you have to do, you have to diagonalize that matrix so that you have only non-zero values along non-zero, or it can be seen that okay, some diagonal element can be 0, but all of the elements cannot be 0 along the diagonal, and the other elements except the diagonal elements has to be 0, so that the matrix can be considered as a diagonal matrix. And to do that diagonalization, we have already a routine in the form of DSYEV, which is within the LAPACK software, and that LAPACK software also needs the installation of BLAS software. Okay, so it will calculate the eigenvalues using that part, and then we are going to write all those eigenvalues, not all those, the lowest 3 eigenvalues, let's say ground state, the first excited state, and second excited state. Okay, so I don't need to find out this part right now, because we don't have to find out the wave function, this part for solving the questions given in the assignment. Okay, so okay, Shomitra, an issue?
Yes, sir.
Okay, fine. So let's move on to this part. So I have already told what I did in this program. So okay, so first of all, so you installed these two libraries, BLAS and LAPACK.
Yes.
So it is working properly.
No, it is not working. I have to see my laptop. It is not
So
working.
you have Windows or Ubuntu?
Ubuntu.
Okay, so okay, so there are so many documentation that how to install BLAS and LAPACK, and how to
Yes, yes.
give the paths, right? So basically I have used this way, that I have downloaded the files BLAS and LAPACK 3.10 something from these two sites, and then I go to the BLAS folder and execute, just open the terminal at BLAS folder and tell that make. Okay, so to compile all the potent files within the BLAS folder. Okay, so what after that I have done, that I have moved this .a file, which will be generated after the compilation, to be libblas.a, to rename the created library. And then what I have done, that we have make a copy of that libblas.a to the user local library directory. Okay, so I have now this libblas.a within our library path. Okay, after that So we have successfully installed the BLAS package and also given the path which will be necessary to work with the BLAS package, and then switch us to the LAPACK directory and adjust the file make.inc. So you may find out that the file is named as make.inc.example, so you have to rename that file to be make.inc, and then you can type this command make. Okay, so that will give you some, I mean, .a file, and then you have to copy that file also to the library directory. Okay, so this will install the BLAS and LAPACK. So the problem which you can face while running this, to solve this problem, this given problem, I will discuss that also, because I was also facing some problem while I am trying to execute. So okay, the subroutine will have something, right? So you see that there is a job set which will have in v. There are two things. So what is done in our codes is I am asking for v, so that will give that okay, I am trying to find out eigenvalues as well as the corresponding eigenvectors. So if we are interested in only computing the eigenvalues, I can tell that okay, instead of v in our code, here, sorry, here we can assign the n also. Okay, just a second. Yeah. So n here instead of v, and then u and l. So whenever we are going to diagonalization, you see whenever we have done it analytically, so either we are going to take it as upper triangular matrix or lower triangular matrix, right? This is the way by which we make the elements, the except the diagonal elements, to be 0 one by one, right? So here in this code it is using upper triangle to be 0 initially. Okay, so after that n is a integer, so that is the order of the matrix A which we are going to diagonalize, right? So if we look at this code, so that will be depending upon npw, okay, number of plane waves. So after that, so the other things are given as here also, so I'm not going to define or discuss all the things. This is pretty straightforward because this is a very well written routine. You can find out everything here. So then if we move on to this part, so initially I was pretty surprised because the values which I was expecting, because the values which I am getting by execution is not matching with the given options. So what I did is I just cross checked. Okay, so what I found is let me just put the slideshow here because this is very, so is it visible, Shomitra?
Yes, sir, it
Yeah.
is visible.
So initially what I am doing that okay, I ran the code. So the code was asking for the values like I have to give the v to be 1, b to be 2, and a to be 15, n to be 100. So you see here so this is what the code was asking, this part, the lowest eigenvalue, that is the eigenvalue corresponding to ground state. So I was not finding the exact answer, so this is pretty different from the given options. So I was thinking that maybe I'm doing something wrong, so I just cross checked with the given values in the lectures itself. Okay, so again v0 is taken to be 0, b is 2, and this is a screenshot of Dr. Prosenjit's course VirtualBox. So you see that if a is taken to be 5, n equals to 5, then the lowest eigenvalues are these ones, right? So I also tried the similar thing, so that is given me the same answers. And then what happens, that again I have using the 510 also, that is the same thing. 520 is also giving me same thing. So that will give us that okay, we are not going we're not doing anything wrong. Maybe the answers there is wrong, something is wrong with the answers. Okay, so if we move on to the questions, you see that sorry, yeah. So the first question was asking for 15 and 100. So I don't find any value which is exactly the same. The closest value is minus 4.45, and that is close to this value here. So I just click it. So not the exact option is matching. So maybe this year they may do some difference and they may correct the options. I don't know what will happen. Okay, and there is also a second option. So you see here is some typo also. They are saying that n is taken to be similar as the question 4, and then n is reduced. So either this is a or this is a. So then we have to calculate the first excited state. So again what I have done, that I have taken two things. One is V naught and B is already fixed. Now I can't make that whether it is A which is changing or N which is changing. So what I did is just take that A. Okay, this is already done. So now keeping A fixed, I have taken N to be 5 instead of 100. So that will give an excited state to be value of 0.07. Okay, now keeping uh, n fixed to be 100 as the first question, I have decreased the value of a to be 5. So that will give us 1.19. In both cases this will not be the exact the answers given, but we have already cross checked that whatever we are doing is exactly the same done by Dr. Poshinjit Ghosh. So it's correct whatever we are doing. Okay, so okay, now the issue what I have gone through when I was trying to run these things for the first time. So for the first time you will have some problem, and after that you can run in this way. So initially what happens, that I was just taking from this, I was not mentioning this libblast.app and lapack.app. So that is the mistake for first time I have done. I don't know whether it will be the same thing when you try to execute that. So that was the problem I was facing. So I was just saying that that can be a problem. So this way, for the first time what I've done, that I have written this libblast.a, lapack.a, and after this, whenever you are going to try these things, you don't need to write those things. It is already taken. So this will be the way you can write. And if you see the same execution profile taken by Dr. Pushenjit Ghosh, you see that he might not use that LAPACK thing, but I have to use it. Without that I cannot compile it in the same way. Okay, so this is how I have done these things. Okay, okay,
Yes,
Shomit, any
yes, sir.
problem?
No,
Yeah, so you may found that the values may not match. but you can similarly, as I have done, you can cross check those things, that whether the code is
Yes.
running properly. Okay, so that's it, nothing else is there. Okay, so thank you for your time.
Okay.
Okay, stop.